We're told an athlete takes a deep breath, inhaling 1.85 liters of air at 21 degrees Celsius and 754 millimeters of mercury. How many moles of air are in the breath? How many molecules? So pause this video and see if you can figure this out on your own. All right, now let's work through this together. So let's think about what they are giving us and what we need to figure out. So they are giving us a volume right over here. They are also giving us a temperature right over here. They're also giving us, I'm trying to use all my colors here, they're giving us a pressure, and they want us to figure out the number of moles. Let me use a green color here. So they want to know, so we often use the lowercase letter n to represent the number of moles. And so do we know something that connects pressure, temperature, volume, and the number of moles? Well, you might be thinking of the ideal gas law, which tells us that pressure times volume is equal to the number of moles, N, times the ideal gas constant, R, times temperature, T. And so we know everything here except for N, so we can solve for N. I know what some of you are saying. Wait, do we know R? Well, R is a constant, and it's going to be dependent on which units we use, and we'll figure out which version of R we use. But that's why I gave you this little table here, this little that you might see on a formula sheet if you were taking something like an AP exam. So we actually do know what R is. So we just need to solve for N. So to solve for N, you just divide both sides by RT, and so you are going to get that N is equal to pressure times the volume over R times T. R times T. And so this is going to be equal to what? Well, our pressure is 754 millimeters of mercury. Now, over here where they give us the ideal gas, or the different versions of the ideal gas constants, you don't see any of them that deal with millimeters of mercury, but they do tell us that each millimeter of mercury is equal to a torr. If you get very, very, very precise, they are slightly different, but for the purposes of a first-year chemistry class, you can view a millimeter of mercury as being a torr. So you can view the pressure here as 754 torr. So let me write that down. So this is 754 torr. And then we're going to multiply that times the volume. And here they give the volume in liters in several of these. And we're probably going to be using this one, this version of the ideal gas constant that has liters, torr, moles, and Kelvin. And so let's multiply times the volume. So times 1.85 liters. And then that is going to be divided by the ideal gas constant. I'll use this version because it's using all of the units that I already have. I know what you're thinking. Wait, the temperature is given in degrees Celsius, but it's easy to convert from degrees Celsius to Kelvin. You just have to add 273 to whatever you have in degrees Celsius to get to Kelvin, because none of these are given in degrees Celsius. And so I will use this ideal gas constant. So this is going to be 62.36 liter torr per mole Kelvin. Mole to the negative 1 is just 1 over mole, so I could write it like this. Kelvin to the negative 1 is just 1 over Kelvin. And then I'm going to multiply that times the temperature. So times, what is 21 degrees Celsius in terms of Kelvin? Well, I add 273 to that. So that's going to be 294 Kelvin. And we can validate that the units all work out. This liter cancels out with this liter. This torr cancels out with that torr. This Kelvin cancels out with this Kelvin. And so we're going to be left with some calculation, and it's going to be 1 over moles, or it's essentially just going to simplify to just being a certain number of moles. And so let's get our calculator out to figure out the number of moles in that breath. So N, I keep using slightly different colors. So N is going to be equal to 754 times 1.85 divided by 62.36, and then also divided by 294 is equal to this thing. And let's see how many significant digits we have. We have 3 here, 3 here, 3 here, 4 here. So when we're multiplying and dividing, we just want to use the fewest amount that I'm dealing with. So I want to go to 3 significant figures. So 0.0123 significant figures. So 0.0761. This is going to be 0.0761. And I could say approximately because I am rounding, but that's 3 significant figures there. So that's the number of moles of air in the breath. Now the next question is, how many molecules is that? Well, we know that each mole has roughly 6.022 times 10 to the 23rd molecules in it. So we just have to multiply this times 6.022 times 10 to the 23rd. So if we could write it this way. We could write 0.0761 moles, all right, mole, times 6.022 times 10 to the 23rd molecules per mole. Now these are going to cancel out, and I'm just going to be left with molecules. And I can just take that number that I had before, because it's nice to be able to retain precision until you have to think about your significant figures. And so, but once again, because we did this whole calculation, we're going to want to round everything to 3 significant figures. So let's just multiply this times 6.022. EE means times 10 to the 23rd is equal to that. And if I round to 3 significant figures, because my whole calculation, that was my limiting significant figures, I have 4.58 times 10 to the 22nd. So this is 4.58 times 10 to the 22nd molecules. Squeeze that in there. And we're done. We're told that a weather balloon containing 1.85 times 10 to the 3rd liters of helium gas at 23 degrees Celsius and 765 torr is launched into the atmosphere. The balloon travels for 2 hours before bursting at an altitude of 32 kilometers, where the temperature is negative 44 degrees Celsius and the pressure is 6.51 torr. What is the volume of the balloon just before it bursts? So pause this video and see if you can figure that out. All right. So you might already have an intuitive sense that this has something to do with the ideal gas law, because they're giving us a bunch of pressures, volumes, and temperatures, and the ideal gas law deals with that. It tells us that pressure times volume is equal to the number of moles times the ideal gas constant times temperature. Now, what's different about this example is that they aren't just giving us several of these variables and asking us to solve one of them. They're talking about these variables changing and how that might affect other variables. And so one way to think about it is, if we divide both sides by T, you get PV over T is equal to NR. And in this example, as this balloon goes to higher and higher altitudes, the number of moles does not change, and the ideal gas constant does not change. So one way to think about it is that PV over T has to be constant. So our volume and our temperature could change, but because this whole expression on the left has to be constant, that could then determine our pressure. Or another way to think about it, you could say your starting pressure times your starting volume over your starting temperature is going to be equal to the number of moles times the ideal gas constant, which also needs to be equal to your pressure right before it bursts times the volume right before it bursts divided by the temperature right before it bursts. Or you could just say that P1 times V1 over T1 is equal to P2 times V2 over T2. And so what are these different variables? Well, let's first think about P1. So pressure at time 1 is what? It's 765 torr. 765 torr. And what's P2? That's the pressure just before it burst, and they tell us it's 6.51 torr, much lower pressure, which makes intuitive sense. We're at a higher altitude. 6.51 torr. Now, what is V1? Well, they tell us that right over there. That is 1.85 times 10 to the 3rd liters. Now, what is V2? Well, that's what they want us to figure out. What is the volume of the balloon just before it bursts? So I'll put a little question mark there. And then last but not least, what is T1? Well, they tell us the starting temperature is at 23 degrees Celsius, but you have to think on more of an absolute scale and deal with temperatures in terms of Kelvin. So to convert 23 degrees Celsius into Kelvin, you have to add 273. So this is going to be 296 Kelvin. And then what is T2? Well, T2 is negative 44 degrees Celsius. If we add 273 to that, let's see, that's going to be, if we subtract, it's going to be in my head, 229 Kelvin. And so we have everything we need in order to solve for V2. In fact, we could solve for V2 before we even put in these numbers. If we multiply both sides of this equation times T2 over P2. And the reason why I'm multiplying it times this is so that this cancels with this cancels with that. So I have just V2 on the right-hand side. Of course, I have to do that on both sides. T2 over P2. I am going to get, and I'll now color code it, I'm going to get that T2 times P1 times V1 over P2 times T1 is equal to V2. So we just have to calculate this right now. Let me give myself a little bit more real estate with which to do it. And so we could write that V2 is equal to T2, which is 229 Kelvin, times P1, which is 765 torr, times V1, which is 1.85 times 10 to the third liters, all of that over P2, which is 6.51 torr, times T1, which is 296 Kelvin. And we can confirm that the units work out. Torr cancels with torr, Kelvin cancels with Kelvin. So we're just going to have a bunch of numbers, a calculation, and the units we're left with is liters, which is good because that is what we care about when we care about volume. So this is going to be equal to 229 times 765 times 1.85 times 10 to the third divided by 6.51 divided by 296 is equal to this business right over here. Let's see, we have 3 significant digits here, 3 significant digits here, 3 here, 3 here, and 3 there. So our answer is going to have 3 significant figures. So it's going to be, if we round, it's going to be 168,000. And so we could just write that as 168,000 liters. Or if we want to write that in scientific notation, we could write that as 1.68 times 10 to the 1, 2, 3, 4, 5. So let me write it that way. So this is going to be equal to 1.68 times 10 to the 5th liters. And I always like to do a nice intuition check. Does that make sense? So our starting volume was 1,850 liters, and then our volume got a lot larger because we're going to a much higher altitude, and that does make intuitive sense to me.